Section 7C talks to us about expected value and this idea of large numbers. So when we looked at the spinner, and we noticed that when we spun this spinner only one time, we weren't anywhere close to the theoretical probability. But after we spun it 500 times and then 1,000 times, we got closer and closer to the expected or the theoretical probabilities of rolling a die, which was 16.7%. So the idea of if we only toss a coin 50 times versus 5 million times, we're getting closer and closer to that theoretical probability. So we use that when we talk about this idea of expected value. So expected value is the amount of money one is expected to either gain or to lose while playing the game. So in terms of Las Vegas, everybody is expecting, hopefully they're expecting to lose, and when they win, they're happy about that, because in fact the expectation should be that you're expecting to lose. And when you calculate it, you're calculating the odds for times the probability, and then the odds against times the probability, and so on and so forth. It'll make more sense once we get to this first example. So you are given 15 to 1 odds of rolling an 11 while playing the game of craps. And so again, remember that odds is not probability. Odds is really money. Okay? So when we do this, we're thinking in terms of the fact that this could be like $15 and $1. So would you expect to win or lose money in one roll? Well, we want to calculate this by looking at how we are going to figure out, and then what happens in 40, and then what are the actual odds to this. So if we are given the 15 to 1, then would we expect to gain or lose? So we're going to take the expected values calculated by the odds times the probability of rolling that, the 11, plus the expected value against it, or the odds against rolling the 11 times the probability that you don't roll. Okay, so again, $15 is your winnings, where $1 is your bet. So you're going to lose that. So when you do the calculation, you get 15. So that's our 15 from our $15. The probability of rolling the sum of 11. So if you look on that sum table again, you'll see that there's two ways to get the sum of 11. A 5 or a 6, or a 6 or a 5. And that's 2 out of 36. Plus the $1 that you're expected to lose times the probability that you don't get an 11. Well, if we're going to get 2 out of 36 to get the 11, then 34 out of 36 is not an 11. So 30 out of 36, 34 out of 36, we subtract those, and so we end up with negative 11, which means we are expected to lose 11 cents per game over the long run. Okay, so what happens in 40 rolls? Well, if you're expected to lose 11 cents per game, then in 40 games you're expected to lose $4.40. So then what are the actual odds of rolling the 11? So remember, odds are the probability for the event divided by the probability, so we don't want to put 4, but just the probability that the event does not happen. And so the probability of rolling 11 is 2 out of 36. The probability of not rolling an 11 is 34 out of 36. So that becomes 36's divide out, and we end up with 2 out of 34, or 1 out of 17, so that's a 17 to 1 odds. So they're giving us 15 to 1, so they're shorting us $2 each time we were to play this game. Okay. So therefore, the house makes $11.11 after 100 games if the bet is $1. This means that the house has an 11.11% advantage over you on that particular game, rolling that particular time. So before I go on with PowerPoint, let's look at the worksheet that we had. And so this is the expected value. So if we have a 100% chance of gaining $1 million, so $1 million and the probability of that. So the expected value is equal to $1 million times 100%, which means we're expected to gain $1 million. 10% of gaining $2.5 million, so the expected value here would be $2.5 million times the probability that it happens, an 89% chance of gaining $1 million, so that's something that's in our favor, so $1 million, and that's a 89% chance, plus a 1% chance of gaining nothing. So that means I'm going to get $0, and that's 0.01. So when we calculate this out, we end up with that expected value is. So we end up with $1,140,000. So even though this seemed like it was not as good as this guarantee, it actually, the expected value for doing this, it has a higher expected value than the guaranteed $1 million. So the idea here is just kind of think, which one would you have picked? By just reading those, most of you guys probably would have picked option A, but in fact option B is probably going to give you the best expected value. Again, this is over a long period of time, so you have to decide whether that's something you would want to do. You can do the same thing with the bottom two and see where those fall. Generally, insurance companies are gambling that you don't need them because they want to just continue to take your money, and you never have to. They never have to pay out of their money to pay for anything that happens to you. So let's suppose this is a medical insurance, and that you pay $17.75 every 2 weeks for your medical insurance, and there's 35 employees at this particular company. So we want to find out how much money, what the expected value for the insurance company is after 1 year. Are they going to gain money or are they going to lose money? So in that, 1 in every 5 employees files a $500 claim in that year, and 1 in every 27 employees files a $5,000 claim. And so we want to set up the expected value for this. So first of all, we want to find out what is the insurance company expecting to make off of its employees. So it's $17.75. There's 35 employees. Every 2 weeks, 26. So they're guaranteed $16,000. So the expected value is going to be this amount of money. It's guaranteed because everybody has to pay in it. So this is 100%. And then if you recall, we have a $500 claim. 1 in 5 employees does that, and a $5,000 claims, and 1 in 27 is the probability of that happening. Again, the odds are the money, or the probability is what we're multiplying. And when you do that calculation, the insurance company is expected to make $15,867.31 in 1 year.